Hi everyone, my name is Natalie. I'm a grad student at Johns Hopkins, and I'm really excited to talk with you all about some of our work that we're doing to try our best to characterize either your favorite exoplanetary system or your least favorite exoplanetary system, TRAPPIST-1, specifically TRAPPIST-1e, in the face of a very active star. So this is work done by a huge team. As you can see, there's a lot of names on here. Specifically the TST DREAMS GTO program, as well as our new GEO program that I'm going to talk about today. So thank you to literally all of them. They're all very important to this work. So I'm going to go through the introduction really fast because Ben's already done a really good job of introducing a lot of this. Same with Caroline, who we heard about from the other day. But today we're going to be focusing on the middle planet in the TRAPPIST-1 system, TRAPPIST-1e, which you can see from this beautiful Travel Bureau poster that we have, is a very popular planet. And part of the reason for that is because it is, by many metrics, the most Earth-like planet in the TRAPPIST-1 system. So, kind of moving back one step from that, you heard yesterday from Caroline that like 400 plus JWST hours have already been invested in the system, and especially for those of you who don't do transmission spectroscopy, you might not understand why that is. And I just want to really point out that this is our best, and depending on who you ask, only chance to really observe the atmosphere of a temperate, habitable zone rocky exoplanet with JWST, and that's only because the predicted atmospheric feature sizes are something from like maybe tens to, if we're lucky, 100 parts per million, which is small but doable with JWST. And that's really only because of how insanely small TRAPPIST-1 is. We've been talking a lot of numbers, but I think a visualization does this really well. TRAPPIST-1 is like approximately the size of Jupiter, and that means that a planet the size of Earth looks so much larger in comparison. So, as I don't think I really need to explain to this crowd, but I will a little bit anyways, TRAPPIST-1 being small is what makes it so important for transmission spectroscopy, but it's also a huge problem when it comes to trying to do that transmission spectroscopy. And that's because these small stars have very strong magnetic fields that don't really seem to die down, and that creates strong magnetic activity. It creates surface features, things like spots and faculae and plage and all those fun things that I'm just going to call spots generally because we don't really know what they are, as well as flares. And that causes tons of problems with transmission spectroscopy because, like Ben described earlier, we are inherently assuming that approximately the transit chord is the same as the rest of the photosphere. If that's broken, big problems happen. And I'm showing a picture of our own sun because unfortunately we don't have a nice picture of TRAPPIST-1's surface. But if the sun is a relatively inactive star and can look like this, imagine what TRAPPIST-1 might look like. So this is kind of all in theory, but we see this very well in spectra as well. So I'm again showing the observations from Olivia Lim's TRAPPIST-1b program and pointing out that we know from thermal emission observations that TRAPPIST-1b probably doesn't have a significant atmosphere of its own. It's consistent with a bare rock. And so because of that, we can be pretty confident that the features that we see in this spectrum are from the star. All of the bumps and wiggles, all of the differences between the spectrum, all the star changing. This, I think, is not necessarily super unexpected. These observations are with nearest SOS, which covers like 0.6 to 2.8-ish microns. And this is like where, for example, we're seeing a lot of activity in the past with HST and ground-based observations, all of that. But unfortunately, I'm now showing observations with near-spec prism, which goes all the way to 5 microns, and that contamination does not necessarily die down at the longer wavelengths. These are observations of TRAPPIST-1e taken with the TST DREAMS GTO program, PI'd by Nicole Lewis. And you see that we see similar signals in the shorter wavelengths, these really strong slopes that are indicative of the temperature contrast between the spots. But as you move out longwards of 3 microns, which is kind of the most important part of the atmospheric range, this is where things like methane and carbon dioxide are expected to be, you see that we also see significant variations in the wavelength there. And you might ask, well, can't you model this away? And unfortunately, not very well. I'm showing our best efforts to model the stellar contamination across the near-spec prism wavelength range. I'm now showing one additional visit. So the first visit is, the first panel is 2 different observations, then 1 each in the next panels. And I'm going to point out a few things first. Like I've said, stellar contamination is across the entire wavelength range. There's no calm wavelengths that we can look to and hope to just get lucky and not be impacted. Second, and I think this is really important, our models are unable to match both the kind of 1 to 3 micron region and the 3 to 5 micron region together. We can overestimate the signal in the kind of 1 to 3 micron region to fit the 3 to 5 micron region, but we will get it wrong one way or the other. And also importantly, especially for my observers in the crowd, there's been this idea for a long time that we can kind of take the shortest wavelengths, use that to predict the stellar contamination in the longest wavelengths, and that can be used to plan observations or whatever. But unfortunately, what I'm showing in the middle panel in the dark red line is if we only show, for example, shortwards of 3 microns, similar to NIRIS, we show that part of the spectrum to the stellar contamination retrieval and ask it to predict what it sees in the longer wavelengths. You can see it does a very poor job of predicting what's going on. So basically, this all comes down to the fact that our ability to model stellar contamination in these observations is model limited. And this is a big problem. We've been hearing from lots of people all over the M-dwarf kind of problem. But better models are being worked on. But we're a little bit impatient, so in the meantime, first I'll say, check out Anna Glidden's poster if you haven't already. I'm talking basically entirely about the star in this talk because the spoiler from these observations is that we weren't able to constrain, say, solar system composition atmospheres for the TRAPPIST-1 planets. But she can tell you all of the problems with trying to then do atmospheric characterization on top of all this stellar noise. But to go into kind of the observational way to deal with this in the meantime while we wait for all these great stellar models, Ben already introduced this idea, so I'll go through it very quickly, but there's been this idea floating around the community of using close transits of multiple planets in order to model independently correct for stellar contamination. And that's because as long as the surface of the star doesn't change significantly between the observations, the stellar contamination signal in both spectra will be the same. So if you, say, take the ratio of the transmission spectra between the two observations, you will be able to use the no atmospheric signals from TRAPPIST-1b, meaning it's only stellar contamination signals, and be left with only the atmospheric signals from TRAPPIST-1e. We did a bunch of simulations, and we found that if you did this 15 times, you could detect an Earth-like CO2 feature on TRAPPIST-1e. So Nestor Espinosa and I proposed this to JWST Cycle 3. Very luckily, we were successful, so we now have 15 observations over the next 2 years, the next 2 cycles. It's about 130 hours of observing time to do our best to figure out TRAPPIST-1e, but also to figure out TRAPPIST-1 itself. So I've marked where we are in this plot right at the beginning of 2025, so you might see we've already had our first observations, which I can show you now. There's a lot going on in these observations. They're a lot messier than maybe what you expect to see from transmission spectroscopy because they have these 2 transits, and each of them, E is transiting first and then B. Especially our first observation back in July has a pretty big flare in the middle, which I will be talking about more later on. There's also a transit of D. There's so many planets in the system that they kind of just pop in and out sometimes, but we're very aware of where all the planets are, so we're careful that they don't say co-transit. But yeah, a lot going on. But say if we take a clearer observation, like the one on July 11th, and we look at the transmission spectra ratio, so this, like we said earlier, we're getting the spectrum of B and the spectrum of E, and then we take the ratio of those transmission spectra, we get a flat line, which is actually good here. I know, especially for people who do transmission spectroscopy, especially of small planets right now, flat lines have been a little bit frustrating, but this is actually good that it's flat because it means we're getting rid of the stellar contamination. So this is essentially telling us that we're doing a relatively good job of getting rid of the effect of surface features on the star, which is good. That's kind of what this technique was meant to do. However, the time-sensitive component of this is still a big problem. Similar to what we saw in the last talk, I'm now showing H alpha in the top panel and a continuum wavelength in the bottom panel. The continuum wavelength is just approximately around 2 microns where we have good signal to noise. And you can see that in our first observation, say, where you could see this very obvious flare in the white light curve, it is very visible in H alpha. But depending on how you look, you might see that there are little bumps and wiggles outside of that huge flare too. However, if I then show you an observation that when I showed you the white light curve may have looked pretty clean, if you look at H alpha, it seems like there is still flares going on there. Depending on how you count, maybe 3, 4, 5 flares going on, which is more difficult because the problem with flares is that they're changing the stellar surface on a very short time frame, which breaks the inherent assumption of our method of stellar contamination removal. I'll also say there's also rotational modulation we think that's going on here. For those of you who do a lot of data analysis, you'll know that near-spec prism has an instrumental slope that goes down in time, but we see an upward slope with time here, which we think means rotational modulation. So even on these relatively short time scale of observations, this observation was about 8 or 9 hours, we're still seeing rotational modulation. So that might sound a little bit scary, but I promise it's not. We proposed for this idea of stellar contamination removal using the ratio idea, but it's very optimistic to say the star isn't going to change at all between the observations. So we're preparing to use other methods of stellar contamination modeling. The first that I'm showing here has to do with modeling our observations at the light curve level. So the idea, similar to what we heard again in the last talk, is building up a model of the star that we can then fit, say, the rotational modulation, the flares, the transits themselves, all self-consistently. We're working on this with Brett Morris and his Fleck model. And the second, which is a little bit less or more agnostic, I guess, about what exactly is going on in the spectrum, is treating stellar contamination in the spectra itself as a Gaussian process. So we use GPs everywhere in our analysis of exoplanets. Why not treat the stellar contamination in the spectra as a Gaussian process and then fit a common underlying atmospheric model? And you will see initial results of that in our first paper coming out of the program pretty soon. The last thing I kind of want to leave off with is, first of all, please be patient for our observations. 15 is a lot. These close transit events don't happen super often, so it's going to take us another 1.5 years to get them all. But one thing that's pretty unique about these observations is because they are very specific events, these close transits, that means we know exactly when they're going to happen. These, well, I'm looking at Jeff, modulo, potentially problems with scheduling with the telescope. Yeah, right? But we know approximately when they're going to happen. So for those of you with ground-based observing time or who have ideas for possible simultaneous observations, please let me know. Usually JWST doesn't let us look at these super active stars, so this is a really good chance for us to try to characterize the stellar contamination the best that we can in this system so that they'll let us keep doing it in the future. And I'm out of time, so I will leave up my takeaways and take any questions.
Hi, Natalie. Super cool. So in an earlier slide when you talked about kind of the stellar contamination model from NIRISS not predicting kind of the like near-spec wavelength ranges, how close in time, though, were those transits taken? Were they like back-to-back transits, or was it like a much broader expanse in time?
That's a great question, but I might not have explained this very well. What I'm actually doing in the middle panel here is I'm acting like we had that the shortwards of 3 microns here was its own nearest observation.
Oh, okay,
like
yes, I understand. Yeah, okay.
Yeah, and then tried to see if it could then predict the longer wavelength stellar contamination.
Hey, Natalie, great talk. I'm really excited for your June and July run. What kind of ground-based support would you want to understand the star, especially since it looks like you're getting a few rotational phases of the star?
Yeah, thanks for bringing this up. This is one of the reasons we're really excited about these observations. For those of you who don't think as insanely about TRAPPIST as I do, the rotation period of TRAPPIST-1 is like 3.5 days, and the orbital period of planet E is like 6 days. So we're actually going to be like sampling essentially the same part of the stellar surface with all these observations, which is very exciting to look for evidence of additional evolution and modulation and stuff. We already have, Ignacio Ribas is already doing some ground-based observations for us. I'm not entirely sure what the exact specifics of those are right now, but lots of ground-based monitoring, but a lot of it is a much longer baseline, so it's characterizing the star over months and months. So I think one of the things we're really interested in is, like we heard great talk earlier, that potentially high-res observations could be a really good thing to use to disentangle some stellar signals and stuff, but I have very little experience with that, so looking for help from others.
Thank you.
I'll make it so given how much variability you're seeing, do you think 15 transits, events, pairs will be enough to achieve your science goals? Or Yeah.
I think so. I say when we only have 3 out of 15, and
Yeah.
I'm feeling a little optimistic. But actually, so what we put in the original proposal, this 15 transits to detect a CO2 feature was about as dumb of a way of doing this as possible. We basically took the transit depth inside of the CO2 feature, the transit depth outside of the CO2 feature, saw if we could detect that at 3 sigma. We've now done a lot more like retrievals and actually looked through, and when you add in, for example, potentially other atmospheric features, that really boosts the detection significance such that we should be able to, we have a few that I think even if we have those big flares like we have, we should be able to kind of work around. So we have a bit of a buffer.
Awesome. No, that's fantastic. All right, thanks everybody for a great session. Thank you, Natalie.